So this is video B of the geometric series unit, and in objective 3 we are going to understand how series apply to salaries and annuities, and how it's very helpful in managing your money. So in 2014, the state of Alaska salary pay of a range 16, which is an employee that most likely has a college degree and is a new professional into the workforce. They start as an annual salary of about $53,040 with an average annual increase of 2.5% each year. If you were to start a job as an IT professional this year and worked for 30 years, what would your lifetime salary be? So we are going to go ahead and use our summation formula for a geometric series, and let's go ahead and break this down and show you how this really is a geometric series problem. So in year 1, you're paid $53,040. In year 2, we have your base pay times your annual increase of 2.5%. So that would relate to 1 plus 0.025, which is 1.025. And then for year 3, if we were to continue on here, you have your base pay times 1.025 squared. So now I want you to note that the relationship between n, or our number of years, and the relationship between r, or our rate, compared to that position is n minus 1. And so this really is a geometric series if we were to add all of these values per year, because you are increasing every single year. So we have our A sub 1, our starting point of your base salary, and R is our wage, our increase, our wage here, so 1.025. We have to have that 1 there, by the way. And N is 30. We are trying to find what our value is after 30 years of working. And so if we were to plug in what we know here into our summation formula, we end up with 53,040 times 1 minus our common ratio here to the 30th power, all over 1 minus 1.025, and crunching that out after working 30 years, the sum of all of your salaries would be $2,328,600. And that seems like a very large amount. We do have cost of living that prevents you from saving all this, but that would be the answer. So we are going to go and talk about additional ways to save money, how we can use geometric series to take a look at what we can invest into our future. And so please turn to page 8. So an annuity is a sequence of equal payments made at equal time periods. We have annuities and savings and investment accounts where every single year for a certain period you make regular payments into the account. Plus, you can also accrue interest on that payment. So in a previous unit, we worked over compound interest formulas. So we have A equals P times 1 plus R to T, where we had our initial payment and our rate and time to find the value of an annuity after a certain number of years. But with an annuity, we are actually taking the sum of all of the different payments. So just an example, you can go ahead and open an account and have one payment, and we can go ahead and calculate the value of that investment after, I don't know, 10 years or so. And that's not considering any additional payments added. In an annuity, we continue to keep adding money into that account. So we are taking into account years of accrued interest, and this ends up becoming a geometric series. Okay, so let's go ahead and write that definition. The value of an annuity, which is compounded n times per year, is the sum of all deposits plus all interest paid. And the formula to calculate the value of an annuity is that first deposit times 1 plus r over n. So we have the compounded interest here, whether it be compounded 12 times a year or just once a year, to the n times t minus 1. And all this is over r divided by n. So the key features that we want to note is how many times is this annuity compounded each year, how many years, or what's the time period that we're looking at. Of course, we have our interest rate R and our initial deposit or payment down. So let's go ahead and go over example 9, which is a nice example of a deposit of $50 that is made on the first day of each month in a savings account that pays 6% interest compounded monthly. So I'm going to go ahead and write the information in the pieces that I know. I have my initial payment, I have my interest rate, how many times the money is compounded each year. So that is 12 times because it's every month. And we are looking at 2 years. So plugging this into the formula that we just listed above, we can plug in 50 where we see an A. And we are going to multiply that by 1 plus 0.06 over 12 and raise that to 12 times 2 is 24. We will subtract 1 and divide everything by 0.06 divided by 12, which gives us the value of 1,271.60. Okay, so on page 9 we have a Got It question number 10, example number 10, and it has to do with your Alaska PFD. I would like for you to pause the movie and answer the Got It question on page 9, which is example number 10. Okay, once you're done with page 9, let's move on to objective 4 on page 10. We are going to find the sum of an infinite geometric series. So we'll take into consideration the first example that we opened up with, but this is an infinite geometric series, and we want to know what the sum of a sequence is that will go on and on and on forever. And we are defining this by the sum, and it can be found actually if the r, or the common ratio, falls in between -1 and 1. We can actually define and calculate out the sum of the infinite geometric series. And this is the first term divided by 1 minus the common ratio. So this is definitely a formula to memorize and be able to utilize. Now, if r is greater than or equal to 1, the infinite series does not have a specific sum. It actually goes on and on forever, and we'll go ahead and define that a little bit later here. So looking at our first example that we opened up the geometric series video with, we have the sequence where we already know that r is equal to 0.1. So we want to find that common ratio if you hadn't found it yet. And the first term is equal to 3. So finding our sum of our infinite series here, so n is not defined, it's just going on and on forever. We have our first term, which is 3, and we divide that by 1 minus 0.1. Now this equals to 3.3, repeating This was also very closely related to the sum of the first 20 terms, but if we were to go on and on forever, this series reaches or is going towards 3.33. I'd like for you to solve example number 12 for the got it. And before you do that, I want to come over to the bottom of your page and briefly talk about convergence and divergence. When a series converges, that means it's getting closer and closer to a real number as n increases. So in our example here, we saw in example number 11 and example 1, we had the summation of the first 20 terms to also equal or nearly equal what the sum of the whole entire sequence or series is. And that's reaching a close, it's closing in to a real number. But if we had a very large common ratio that was greater than 1, it will just infinitely grow, and we call that divergence, or it diverges. It doesn't converge. We can diverge towards infinity or negative infinity, or it cannot reach any number at all. So this concludes the geometric series video.